So last week we were looking at different ways that we can work on our imagery to extract different types of information. We saw how we could extract information from a single band, from a pair of bands, from 3 bands, from more than 3 bands. And today we would like to take our discussion a step further, and we are now coming to the mapping aspects of remote sensing. And so today we want to talk about image. So that's what we want to talk about today. And the idea behind image classification is that the idea behind it is that we want to, in image classification, want to relate values to known and cover. That's what we essentially want to be able to do. So we're essentially saying that so the idea is that you have your image, we want to come up with a map, land cover. Examples of land cover, we can have water, we can have vegetation, have built up areas, or now remember, as you can see, we are talking about land cover. It's very hard many times to map land use, but from land cover, we can make inference about, we can make inference about, so we may have 150. So imagine this is a band from the near infrared region. We want to be able to say the vegetation. So what we essentially want to do is to be able to relate the pixel values to known land cover. That's what we're trying to do in image classification. Now, we have 2 types of classification techniques. I'm sure many of you should know them, and classification and categorizations as we go along. So the idea behind unsupervised classification, with these ones is referred to as clustering, and maybe I should mention is that we want to be able to relate the satellite image values with the known land cover classes, and the algorithms that we use have image classifiers that enable us to relate the pixel value, the DN values with known land cover. So we have, we usually refer to them as clustering algorithms. And the idea is that, so let us imagine we have, on a fresh sheet of paper, let us something hypothetical. We have blue, green, red, and we have our reflectance, and we know that for vegetation it will be something, and we know that for, let's say, for water, something like that, and then for soils, so look at a case where we have a band there and there, band there. For purposes of a discussion, let's have a band there. So when you look at the histogram in red, for example, so we get our image, come up with the histogram, say our values are from 0 to, we can see that if we get the red band, we can see that the water pixels will be here as well, and then we have vegetation pixels probably there, and maybe, actually, let me put them in their colors, so maybe that will be clear. So let us say in the red, for vegetation in red, or let's start with water. Deleted the wrong thing, 5. So in the red band, as we can see that our water pixels would be probably somewhere there, and our vegetation pixels would have probably be there, There might even be a sort of overlap between water and vegetation. And then if you look at the distribution of the soil, probably there. This is in the red. So let's look what it would happen. Sorry, what would it look like? What would this look like in the infrared? We did a similar histogram. We know that again, your darker pixels, yes, the blue would still be here, and then this time your soil pixels would be probably somewhere there, and then we'd have vegetation somewhere there, 255. Now, if you plotted, so this is near infrared, if we plotted red, we can plot, sorry, this is not, so we have a 0, 5, and then also here 0, 2, 5. We have red against near infrared. Our water pixels, remember, you can see red here, it was low, near infrared it was low. Would have our points there. Then vegetation would be sort of in the middle of red, but high over here, and then our would be there. In actual fact, it doesn't appear as beautiful as this. It's a lot more complicated, but the idea is that when we plot these pixels, one band against the other, can we, and so this is what we refer to as image space. This is what is referred to as feature. So the idea is that when we look at the feature space, can we partition area and then so that we can now relate the pixels to the given land cover classes. So what we have done here is that we know that water pixels are there, vegetation pixels are there, soil pixels are there. But in most cases, when we're doing the plotting, we don't know, and we need to find a way of doing that. So what actually happens is when you do your near infrared to red, it can even be red to blue. The idea is that we have we look at the pixels and look at the distribution in feature space. So this is feature space, and we look for clusters. Now here we can obviously see that there are two clusters, and what happens is that the unsupervised supervision classification, we first cluster, then assign classes. Yeah. So what would happen is that we would have our, this in black. So what would happen is that what happens is that we have the red band, have the near infrared band, get the histogram. Now this is done automatically, you don't need to do our distribution, and then we make a comparison of red, near infrared, and the aim is to identify clusters in feature space. So the algorithms we're talking about will look at the data, and if you say you want two classes are needed, it will look into the data, divide this into two, and then your result will be an image with two classes. Now, after it has divided that into A and B, it will now be for you to now tell us that A is maybe water and B is vegetation. So the best example I like to give is that if I walk into the master's class, I can ask for two categories of people. What would give me examples of two categories of people of how we can divide your master's class? Male and female, very good. Yeah. So so I have said I want two clusters. Now, after I've got those two clusters, we assign each cluster a given class. So that's what we have done here. We have looked into this feature space. We have got the original band, red, near infrared, histogram, plotted them against each other. Say we want two classes. It will divide that into two. Now, there are different class algorithms which operate differently. And there are good ones, there are poor ones. Some of those things you will need to try them out. You could even say, I want three classes, so the algorithm will look into here and probably say like that, and now it will give us the three clusters, A, B, B, B. So it will give us the three classes, and now the onus will now be on you to tell us what those three classes are. So Maybe it is a case of water, then maybe sand, shore sand, and then maybe vegetation. So the idea behind clustering algorithms is that it clusters feature space and gives us the clusters, and then we determine what those ones are. Now, when it comes to supervised classification, here we need to know the classes we need in advance. We then collect or identify samples which we use to, we then collect samples which we use to determine what we refer to as decision boundaries, decision rules, which we now use to classify the rest of. So a good example would be I come to class, I pick an example, or this is an example I like using. I want to come up with a supervised classification algorithm for distinguishing between male and female, and I say I'm going to measure height against weight. So what is going to happen is that I will pick that's on height, weight, or X1. I measure the height and weight. And because we are dealing with male, female, I have to get samples of male and samples of female. So let us say male, X3, H3, weight 3. Then I also come to female, which I'll say Y1, can say HY1, weight. So I've got a sample of three women and men. So let me use this to represent the women. Generally, they're usually shorter and lighter. So now pick 3, but we could have a good number, and if it is normally distributed, it will be something like that. And then when it comes to the male, so maybe, men are usually heavier and taller, and of course, we also have cases where there's something like that. So from here, we can come up with an algorithm, and from our, I think it's even primary, the equation of that line will be y is equal to mx plus c, and we can now say that decision boundary, so this is our line or boundary. We can now say this is our classifier, weight, height, that's our equation, which we have got from there. We have plotted it here. So what now happens is that I can now use this. I meet an unknown person. I'll measure your weight. I'll measure your height. And if I'll classify you as, and if you are here, if you fall here, I'll classify as. So the point here is that for us to do the classification, started with samples. We got samples of male and samples of female. We got their weights and their heights. We plotted it. And that gave us a decision boundary. So that's our decision boundary. And our decision rule is that, that anything that, any person, if we want to know whether they're male or female, we measure their weight, their height, and if they're this side, we classify them as male. Here, if they're here, we classify them as female. So that is an example of what happens in supervised classification. So relating it to what we do, image classification, we have our 2 bands, having black for this. We have our 2 bands, whichever bands they are. So we have our 2 bands, near-infrared, red, and we get samples of given land cover. So we can get samples of water, we can get samples of vegetation, and we can get samples of built up area. So what are the different classifiers that we have? What are the many? So we have various decision boundaries and decision rules that can come up, i.e. there are so many image classifiers, we can't exhaust them. We just need to have an appreciation of how they work. And so one of the most basic ones is one of those we refer to as the box classifier. So what would happen? What happens is that, okay, so how the box classifier works is as follows. It creates a box around, so it will create a box around the different classes. So it will get the minimum position, maximum, minimum, maximum, minimum, maximum, and then, so that now, this is what we have in feature space. Anything, so we remember we started with the samples, we come up with our decision boundaries. Now we then project all the pixels, anything that falls. So anything that falls here will be classified as water. Anything that falls here will be built up area. Anything that falls here will be vegetation. So we start with the sample, come up with our decision boundaries, rules, and then we end up with our classified image. So we had this, then we just picked a few samples, and these samples were what we used to come up with our decision boundaries and decision rules. And after that, we now have a classified image. As you would appreciate, the challenge with this one is that you might have points outside which will remain unclassified. So when you look at your classified image, you will have your water, built up area, and whatever, but then you'll also have pixels which are unclassified. So this is one of the very simplest classifiers. There are more complex ones. I'll talk about maybe minimum distance to means. So how does this one work? We have our space, we have our water, we have our built up area. Now this is, remember, this is training data. We have our vegetation. This one work? Very simple. Yeah, so how does, I'm now dealing with what we refer to as minimum distance to means. It looks at this data and it marks the mean positions of each class. So we have got our sample data. We have plotted this against the other. And so it will mark the mean position as that, so that now we have the mean position for the first one I've put is the one for water. I'll put the position for vegetation. I'll put the mean position built up area. So when we now have an unknown point, a point which you want to classify, let's say that, what it will do is that it will calculate the distance to all the mean positions, and it will be assigned the mean to the distance to which it has the shortest distance. So it does that calculation and will now assign it that class. So that's how the minimum distance to means works. We have various other classifiers. There are those which look at the probability of these points and assign a class depending on the probabilities. Now, when we are picking this, we call it training data. The sample data is also referred to as training data. What we're doing is that we are essentially training our classifier. We're using the training data to train the classifier. And by training, we mean coming up with decision rules, decision boundaries. We have other types of, now, as you can see with this one, we can get the minimum, maximum, minimum, maximum, minimum, maximum. Here we're getting the mean positions. Others are using probability. And so we have what we also refer to as parametric classifiers. And this may be supervised or non-supervised. So what we have been looking at are what we refer to as parametric classifiers, and they are premised on the fact that we need to determine statistical parameters. We now have a whole suite of non-parametric classifiers, and I'll give you a very simple one. We can have our training data here, and then we have another training data there. There are classifiers which will just look at the best way of putting a straight line through there. So in literature or whatever, you'll hear support vector machines, or you can also have what we refer to as k-nearest neighbor. So what that one does, we have our point here, which we want to classify. What it's going to do is it is going to calculate to all the training data, and it's going to look at the k nearest neighbors, which is always odd. So if k is equal to 3, it will look at the 3 nearest neighbors, look at their class, and classify accordingly. So that's one of the classifiers. And then we also have decision trees. That's another group. Now, with all of these classifiers that I've talked of, your pixel can only have one class. It's either water or built up area or vegetation. We now have what we refer to as fuzzy classifiers, which allow multiple. Yeah, so because you know that if you're looking at a Landsat and you have a pixel size of 30 by 30 meters, chances are that within 30 meters, you may have different classes, but the way it works is that it only assigns one pixel value, one class. With what we have been talking about here, we're talking about, yeah. So with fuzzy classifier, we can say that it has 80% water, 20% vegetation. So that's it about fuzzy classifiers. So where is this important? Where is image classification important? Image classification is important because it is what we use to determine, to measure, to extract information about different land cover classes. And there are numerous applications of this. Being able to identify these different land cover classes has application in forestry. It's what we use to extract forestry areas. It's what we use to extract wetland areas. I'm hoping to get somebody, now that I've talked about image classification, I'm hoping to get somebody to come and demonstration of a project they have done in remote sensing so that you get a broad perspective. I'm also hoping to get somebody to organize some mini practicals so that we can do some of these things practically. At the bare minimum, you should be able to see how to carry out a land cover classification. As for the application areas, they are numerous. We do this, say, we have had people doing monitoring urban sprawl. So for example, if I get images of different dates and I map the different land cover classes, what is the land cover change dynamic on the ground over the past 10, 20 years? Can we see cases where an intervention has worked? Can we see cases where we can make predictions? If we look at how wetlands have reduced over the last 20 years, can we make predictions about what will happen? Or how about a case where we know that wetlands had been reducing, then there was a policy intervention? Can we deduce that the policy intervention has yielded positive results? Satellite imagery affords us that. Now, the other thing that is equally important in image classification is what we refer to as accuracy assessment, because after you have done your classification, we need to be sure that what we have done is accurate. So having carried out your classification, you usually have to carry out accuracy, and what what is the idea behind accuracy assessment is that we want to compare the classified. So that's how we do the accuracy assessment. We look at the map that we have come with, and so we have our classified image, we have our various classes. Of course, the question now is how accurate is this map? And so to be able to know how accurate it is, we need to carry out accuracy assessment. And the idea is that we get mapped points and compare with what is on the ground. Now, there are many ways of doing this. Sometimes if we have done a classification using Landsat, we can use a high resolution image to do ground truth data. We can also go to the field. What that would mean is that we would get some points and randomly pick them, go to the ground, see what is there, and compare with what we have mapped. And so to be able to do that, we do the assessment using what we refer to as an error matrix. Many types of error matrices, but I'll be using the traditional one. And it's a matrix, as you can imagine. And on the top here we have reference, and here we have classified data. We can have water, vegetation built up, and we want to compare the number of pixels that were classified as water and are actually water on the ground. So I'm just going to pick fictitious values. Probably we had 10 pixels, which were on the ground, classified as water, but on the ground or in the reference data, we saw that it was water. We may have had 2 pixels, which were water, but on the ground we found it was vegetation, and maybe 2. So as you will appreciate, the diagonal values represent correctly classified pixels, and off diagonals give us a measure of error. We have what we refer to as overall accuracy. It will be our the diagonal sum of diagonal values over sum of all the pixels. So it would be equal to 10 plus 12 plus 13 over 10 plus 12 plus 13 plus 2 plus 2 plus 1 plus 2 plus 1. So that our overall accuracy is what? That's 25, 35 over 37, 30, 39. And you can see what this is as a percentage, and that will be our overall accuracy. So that's one of the ways in which we can determine overall accuracy. But that's not the only measure parameter we can get. We can also have what we call user accuracy. And for this one, it will be 10 over 14 times 100. This will be 12 over 13 times 100. This will be 13 over 16 times 100. And what does user accuracy mean? User accuracy means that, I don't know, here we have a percentage. Let me get my calculator. Yeah, so here is, this is 81%. This is 71 point. What do these figures, what does this mean? It means that your map, whatever has been mapped as vegetation, there is a 92.3% chance that what's mapped as vegetation will actually be vegetation on the ground. Built up area, what this means is that whatever you have mapped as built up area, there's an 81.3% chance that what you have seen mapped as built up area will actually be built up area on the ground. So we refer to this as user accuracy. Then we also have another term called producer accuracy. It's calculated similarly. So 10 over 13 times 100 12 over. What is the producer accuracy telling us? It is telling us that it's giving us the accuracy with which the algorithm has performed. So with the algorithm that you have chosen, it has a 76.9% accuracy of detecting water. It has an 80% accuracy of detecting vegetation and 86.7% accuracy of measuring built-up area. Now, when you carry out a classification, there are variations of the overall accuracy. There will be the cat statistics, that is K hat. But what it is essentially doing is giving us an overall impression of our accuracy assessment. In which cases we want to carry out accuracy assessment? We will do accuracy assessment when we want to compare classification algorithms. So we have the usual algorithms that we have used. And okay, so Nantes, Sarah is asking if I can use any diagonal of your choice. And now I don't know if you're referring to accuracy
Bluetooth device is ready to pair.
Are you referring to accuracy assessment?
The Bluetooth.
Sarah, I don't know what you wanted to ask. I wanted to, but if it is about this, like I've said, what this one is doing is giving us a relationship between what was classified accurately and what was wrongly classified. And of course, you can imagine you have errors of omission or commission. Here we are saying that water pixels which were correctly classified as water, that is it. We have water pixels which were classified as vegetation. We have water pixels which are classified as built-up area. So it's only the diagonal which is going to give us correctly classified pixels. So let us say that we have these traditional classifiers and one of you has come up with a new algorithm. How do we test it? We will do a classification assessment. We will have algorithm A and B, and then we shall look at the overall accuracy. We shall look at the producer accuracy. We shall look at the user accuracy. So that's one of the times when we shall be, be interested in classification accuracy. We can also do it when we want to compare different imagery types, but we can also do it. So, for example, could you please speak up and so that I can understand what you want to do, what you are exactly asking? Yes, I can hear.
I think Sarah was asking, is it a must to choose this particular diagonal that has 10, 12, 13? Or maybe why do we choose this diagonal? And why not other diagonals? I think that's what she wanted to find out.
Now, this diagonal is showing us the classes which were mapped. So here we are looking at water mapped, which is mapped water, and on the ground it is water. Let us, for argument's sake, let's pick, I don't know what it will tell us because we are only picking interest in here. We're talking about built-up area, which was, or we have classified it as built-up area, but on the ground, it is water. This one is where we have vegetation, which is mapped vegetation. And then here we're talking about, it was mapped water, but reference data was built-up area. It doesn't give us anything valuable. This is specifically showing us correctly. Yeah, so this diagonal is showing us the pixels which were classified correctly in comparison to the reference data. So that's why we're interested in this diagonal. That's what it means. Anything off diagonal refers to wrongly classified pixels. So the diagonal shows us classified image, it was water. When we went to the ground, we saw water. So how many of those pixels were accurately of the reference data? How many pixels were correctly classified? 10. These ones are wrongly classified. We need to get a statistic. We need to know how accurately our work is doing. I don't know if that makes sense. So we also do accuracy assessment to also evaluate our classifier, our classifications. Okay, so when we're doing accuracy assessment, we want to compare algorithms. So for example, it is said that Uganda is going to launch a satellite image into space. How would we evaluate its products vis-a-vis other imagery? So in that case, we would say, instead of the algorithm, we would say, what's the overall accuracy, producer accuracy, user accuracy, which of them maps water better, blah, blah, blah. So that's what we would be doing. So those are some of the instances where we would need to carry out accuracy assessment. But also, to be sure, because you want to know that your classifier is giving you accurate results. And why is that the case? Because ultimately, at the end of the day, somebody is going to make a decision based on what you have come up with. So we need to be sure of the accuracy of what we have got. So you can imagine, supposing we carried out a classification, we have a satellite image. This is 2010, this is 2022, and we have got our wetlands. Our area is 400 square meters, and then here we say 50 square meters. If you have made an error, somebody is going to make a decision based on that error, and it could be catastrophic. It could also be the reverse. So we need to know how accurate are our classifications. So whenever you're doing remote sensing work, remember somebody somewhere is going to make a decision based on what you have come up with. And I'm hoping I can get somebody to give a very good presentation in this regard, how they've used satellite imagery to make certain decisions, and how it is influencing decision making. I'm hoping that this will give you a nice overview of the course and what it's about and what you can do with remote sensing. Unfortunately, we only have 2 weeks to do this. Previously, we used to do this for 3 weeks, and the first 2 weeks would be classes, the last one would be practicals, but it's a crash program, so we have to crash everything. So we can only give you so much. So any other questions before I give you the clip that you will have to listen to? And of course, not today. If we had finished earlier, we would have done it, but this is just something to complement your learning experience. And if you have listened to all of them, it is really concretizing what we have said. So please make time to listen to that video clip to help you understand what we're doing better. And the floor is open if we have any questions. Okay, thank you very much and have a great evening. Let us resume tomorrow.